So a lot of waste material goes into cement manufacturing. I suppose in Brazil it would be the same, but in India we say that if you don't know what to do with it, you put it into the cement. We put it into the cement, you put it into the kiln, everything. Sometimes we have some food product which is rejected by the market, goes into the cement, goes into the kiln. So everything, all sorts of things go into cement, and we have to understand both the calorific content and the emissions. It is not the same as coal when you are putting pharmaceutical waste or paint sludge. Paint sludge is very common to put in there. Yeah? And then we have to know the electricity, because electricity is also energy. And it also has a carbon footprint. So that also has to be brought into account. So what we have to do is a process map. It looks very complicated, but this is necessary. And here you see all the processes. Let me start from the left. So we have to know where the electricity is coming from. Is it coming from a renewable source, or is it coming from coal, or is it coming from diesel? So we have to know where the electricity is coming from and how much. We have to know all the raw materials that are going in. The distance that it's traveling is also important, because when it travels a long distance, that means the carbon footprint is higher from the transportation. So we have to know how many kilometers each ton of material has traveled. So we have to know all the materials going in and this. And the main material is limestone. Okay, we have to know what goes into the extraction of limestone, how many kilometers it traveled. Usually in India, the quarry is very close to the cement plant. It's almost adjacent. Then we have to know the electricity consumption and the fuel. All the fuel, again, the amount of fuel and the distance it traveled before it goes and becomes clinker. And these are the different systems you can consider. You can consider just gate to gate, means only the plant. Because what happens outside the plants is often beyond the control of the manufacturer. But for academic interest, it is better to look at the whole system. But once you have the data, it is easy to do one or the other and see where we can improve. Which process has to be changed, what component has to be changed to reduce the embodied energy and the carbon. So these are some numbers. Some of you will already know the numbers, so I'm reiterating. If we look at energy, out of the 5,300 megajoules per ton of clinker, we use a lot of energy. Most of the energy is coming from fossil fuels, at least in India, at least in this plant. And some of it is from electricity. Okay? This is only for clinker. And look at the carbon footprint. Where is the carbon dioxide coming from? Because of the conversion of limestone. Calcium carbonate converts to calcium oxide, and therefore the CO2 is coming out. And this is 56% of all the emissions are coming because of the conversion of limestone. So instead of limestone, if we use some other material, then this part can be reduced. What is now called decarbonized materials. If we can use decarbonized raw materials, then this will reduce. Other than that, you see that the fossil fuels, when we burn the fossil fuels, we emit a lot of CO2. So that is about 30%. So here we can do a lot by changing the amount of fossil fuels, the type of fuel. If we change it, then that will become better. So now we go to cement. We take the clinker and we are going to make cement. In cement now, we are going to grind the clinker and we are going to add other materials. So I'll show you results for Portland slag cement and ordinary cement. So we have all the part that is corresponding to clinker plus the addition of gypsum. So where the gypsum comes in and what is the type of gypsum also matters. If it is natural gypsum, you have to have extraction, transportation. If it is waste gypsum, then you don't have any extraction, but the distance matters. It goes into the ball mill and comes out as cement. If you have slag cement, then you have to grind the slag and blend it. And you see already a big difference. instead of 855 kg of CO2 per ton, you bring it down to 500. By reducing the clinker and adding slag, already we see a big benefit. So this gives us hope that by reducing the clinker, adding other materials, our cement is going to become less and less carbon intensive. So these are some numbers. So we have the clinker part here, like I showed you before. Major emissions are coming from the limestone, then the fossil fuels, pet coke, which is a waste but still has a lot of carbon emissions. And when you reduce the amount of clinker, you have an overall reduction. We go down from 900 to 670 to 560. This is LC3. LC3 is sort of between these two. Okay? Clearly, less clinker, less will be the carbon emissions and the carbon footprint. Energy has a similar pattern. So when we go from ordinary Portland cement to PPC, which has fly ash, PSC, which has slag, you see that the amount of energy required, that means the amount of fuel required, the cost reduces. LC3 is in between these two because it requires energy for calcination. We are taking the kaolinitic clay and we have to calcine it to 900 degrees or 800 degrees. Not as high as 1500 degrees, but still some energy is required. So with this, we can have a good idea of what are the different impacts of the different cements. Then we go to concrete. You add the cement, you have to add the aggregates, you have to add everything else, and then you can calculate what happens to concrete. So we started with clinker, we made cement, we put the cement into concrete, and we can still calculate what happens. So these are the different types of concrete, energy and carbon dioxide emission. So let's focus on carbon dioxide emission. You can see that what happened in ordinary Portland cement reduces by a third when we go for blended cements. We find that the emissions are slightly higher when you increase the strength, but not proportionally. It is not increasing proportionally. So we have to insist that higher quality, higher grade concrete will overall benefit because you will use less material. Yeah? But we have to know how much it is. So it systematically shows that when you go to blended cements in concrete, you will have benefits. Now, the idea is to put all of this together. And we came up with two parameters. One is the energy intensity. Again, this is inspired by the work of Vanderlei John and Daminelli at USP, where we look at energy divided by strength. We cannot forget strength because we are engineers, we are constructing for safety. So strength is important. So we look at energy per unit strength. And here, when you go to higher grade, this compensates. It tells you how things work out. So here we combine energy and mechanical integrity. Energy can also be thought of as an idea of cost. And you have this nice looking curve, similar to what Vanderlei John has in many of his presentations. As strength increases, the energy intensity comes down. So clearly it is good for us to use higher strength. Because for the same rate of increase of strength, you will require less energy in your concrete. Now, here we don't have durability, we don't have carbon footprint. So we came up with another index, which is provocatively called apathy index. Why apathy index? Because at the site, nobody cares about durability and carbon footprint. This is reality. Academics care a lot. Some people maybe care. Paulo, of course, cares a lot, and maybe his students care very much. But often you find at the site, people are thinking only about strength, inauguration of the building, and that's it. Durability doesn't come. So we said, let's look at a parameter which combines CO2 emission and service life, and came up with this apathy index. The apathy index depends on the attack. So if it is durability, the durability due to chloride ingress or limited by chloride ingress, we divide the carbon emissions by this factor, which depends on the diffusion. Okay? Higher the diffusion, this parameter changes, and therefore your apathy changes. Similarly, we can do for carbonation. And here we have the carbonation factor, which depends on the rate. So we can think of a way of combining all these 4 parameters. Strength is very important, energy is important, carbon emissions are important, and durability is important. Now, can we put all this together and give an easy framework for someone to choose a concrete? So that's what we did. So we took the apathy index, we took the energy intensity, and I think many people, including Paolo, have said that for concretes which have sustainable binders, we should look at a later strength. I think Kasuga-san also mentioned, for sustainability, we should look at later strength. So we've taken the 1 year strength for looking at sustainability. And these are what we see. LC3 comes here, OPC is here. Lower the better. Less apathy, less intensity is better. Okay? And we see that the higher strength is always better. So whichever is in this lowest corner is better for sustainability when you have chloride attack. Now what happens when you have carbonation? The situation changes because the attack is different. And you find that we don't have the same trends as before. Now actually LC3 is the worst. And we find that fly ash comes out better. And again, higher grade concrete is always better. So what we have said for many years, better to go with higher grade concrete, not only for less volume, but also for durability and carbon footprint and sustainability. Okay? So this is the overall picture. Maybe I'll just take 5 more minutes to tell you what we can do about the aggregates. Because I've talked about the binder, I've talked about all these, but what do we do about the aggregates? There is a lot of waste in the world, right? We are going to construct more, we are going to demolish more. What can we do about it? We cannot just crush and put the concrete back into new concrete because it doesn't work. It has very high water absorption. There is a lot of mortar still stuck there. The strength will go down and the compressive strength will reduce. So I'll show you some results where we are trying the process of heating and then crushing. So we heat to about 500 degrees and then we do the crushing with milling or any light crushing to see if we can separate all the important fractions. We have some fraction that has to go back into the furnace, but the coarse aggregate, the fine aggregate, and the fines. So we want to separate all this effectively so that it can go back into concrete. So the idea is to heat the concrete up to about 450 degrees or 500 degrees, then some milling or some crushing, and we find that we can get good recycled concrete aggregates. So these are some results. The top row is pristine aggregates, natural aggregates, granitic aggregates. Then these are the treated ones, comparable. Adhered mortar is very little, only 4%, and much better than just crushing. This is just crushing. And you see that the values are much different. And what is important is the fine aggregate also can improve. In many countries, like in India, we don't have sand. We have used up a lot of sand, so we cannot use more sand. So if we can get the sand from old concrete, what more can you ask for in terms of sustainability? And again, you see that the numbers are reasonably good. Absorption is still high, better, not as good as the river sand and the crushed sand, but much better than just crushing simply without mechanical treatment. Okay? So I'll take 2 more minutes to show you something new that we've just tried out. So before that, so we made concrete, and you see that the strength is almost good. This is 100% coarse aggregate from recycling. No new aggregate was used. 100% from the recycling. The strength is only slightly less. Sand, all the sand is recycled sand. We take from crushed concrete that is thermally activated. There is a slight reduction, but this we can manage. We know enough of chemistry to manage this. And this is for the concrete itself. We put both fines and coarse aggregates and we can get decent strength. We can get a 45 megapascal strength concrete compared to natural aggregate concrete, almost similar. and properties are almost similar. So we can do it. It is possible to recycle concrete into new concrete. One last slide. So what we said is, instead of using electricity, can we use solar energy? So we took this plant, which has these huge mirrors, 64 square meters of mirrors, concentrates all the energy in this container. So this is servo controlled, so it follows the sun and changes shape so that it focuses all the energy here. And they allowed us to play around and put concrete. So we put concrete in here. So you blast the concrete with very high heat for 1 hour, and then you mill it. So that means no electricity, except for operation, no electricity for heating. And we got decent results. So we could do this process, but instead of electricity, we use solar energy directly. We just zap the concrete with a lot of heat for a short period of time and then mill it, and then you can get the aggregates like before. So I will conclude. In my opinion, following from what Dr. Kasuga-san said, for sustainable construction, we need new type of cements, new type of binders. We have to explore. We have to extend durability. Durability is very, very important. We cannot talk about sustainability without durability. We should try to recycle. We should try to recycle as much as possible. It is possible. It will take a little bit of effort, but it is possible. Water. And I think Dr. Charles Namai will talk about water tomorrow. Water is very important, especially in countries like mine. We don't have water for people, but we want good water for concrete. So you take away water from people to make houses for them. So it doesn't make any sense at all. So we are using drinking water for concrete, which doesn't make any sense. Yeah? So we have to lower the water demand. We cannot come up with technologies that require twice as much water. It will not work. It is not sustainable. New systems. We have to look at new reinforcement, new composite systems. So this, in my opinion, will really change and go along the lines of what FIB is doing, what IBRACON is doing, and all of us together can do. Okay, so thank you very much. This is a large part of the group. These are some of the students who have contributed. So always I say that they do all the work, and I get to come to Brazil and talk to all of you. Thank you very much.
Vocês viram que é um querido, né? Fica fazendo referência a nós, aí aos colegas do Vanderlei João e tantos outros aqui do Brasil que a gente aprendeu muito com eles. Ele entende português, por isso que eu vou continuar falando em português e você não precisa falar tradução. Fala espanhol também, é poliglota. Português não muito bom. Ira já tinha comentado isso comigo, que recente ela chegou da Europa, de uma reunião da FIB, e ela comentou que um dos pontos que distingue o concreto de outras opções estruturais é justamente a questão da durabilidade. A gente tem um ganho grande aí, né? A gente sai na frente, o concreto sai na frente. E isso você ressaltou muito bem aqui, muito bem. Esses estudos de durabilidade, o índice de apatia que você propôs, é bem interessante, porque a dificuldade da gente é comparar coisas corretamente, né? Arrumar índices que a gente consiga realmente raciocinar se a pesquisa que a gente está fazendo está caminhando na direção certa. E muito interessante a sua apresentação. Gente, está aberto, então, para questões que vocês tenham, depois desses comentários, para dar uma relaxada aí. Quem quiser fazer uso da palavra. Tem uma mocinha aí de apoio com microfone? O esquema é dar um microfone que deveria estar por aí. Vamos ver se a nossa organização ajuda, para que vocês, se não, vem aqui, se não tem um microfone, vem aqui, por favor, e faz a pergunta. Paulo Fernando, por favor. Quer vir aqui ou você quer falar? Eu acho que... Tem um microfone aí para nós? Por favor. Ira, obrigado. Se alguém...
Bom, professor, bom dia, muito obrigado, excelente palestra.
Obrigado.
Muitas coisas o senhor colocou aí, nós temos praticado aqui no Brasil, né? Meu nome é Paulo Fernando, eu sou diretor da Concremate. A minha pergunta objetiva é, qual é o teor ou a quantidade máxima de escória que o senhor recomenda para que nós possamos colocar no cimento? E qual a quantidade máxima de pozolana que o senhor recomenda também para colocar no cimento? Muito obrigado, parabéns mais uma vez.
Obrigado. So tenemos, we have experience with 3 types of materials. With slag, we have gone up to 60%, 60%. That means the clinker is about 35%, yeah? And 60% GGBS. With slag, we have gone to 30%. With fly ash, Cinsabolante, we have gone up to 30%, 30. And then with limestone calcine clay, we find that at around 45 to 50% is the maximum if you want high early strength. If you are not worried about high early strength, you can decrease the clinker to maybe 35% or 40%. Here we have it 50% because the industry wants high early strength cement. And because of that, we could not go more than 45% of limestone plus calcine clay. Yeah? Obrigado.
Olá. Obrigado, professor, pela sua palestra. Sobre o resíduo da construção civil, que o senhor falou agora no final, o objetivo de fazer uma breve calcinação é para obter alguma pozolanicidade do material ou é para eliminar algum tipo de material deletério? Obrigado.
See, that's a very good question. So what we are finding is the fines can be activated. Can be activated to be used as a SCM. It is also a good raw material for making cement, especially if you carbonate it. So we can allow the aggregates to be outside, say for 3 months. It will take up a lot of carbon dioxide also. So when you are putting back into the concrete, you can minus some of the carbon dioxide that we have emitted. And the fines, we are looking at different ways. There is an international group which is looking at the fines. So a lot of possibilities are there. But also we should remember that we should worry about what was the original concrete aggregate. So if it is limestone, like in Europe, there is almost no problem. You can put all the fines back into the cement. But like in India or some places in Brazil, if you have granite and basalt, then the crushing to put it back into the cement becomes very complicated. So we have to think of other ways of processing. For Europe or for those concretes made with limestone aggregate, it's very simple. You can put the limestone back into the cement kiln and you get new cement. Thank you.
Ninguém se anima aí, gente?
Sim.
Microfone.
Sim.
Espera um pouquinho só para ajudar na tradução.
Ok, desculpa. Já que ninguém pergunta, eu vou de novo. O calcário,
Sim.
o limestone,
Sim.
Ele tem que ser mais fino do que o clinker. A finura, o blend.
See, tiene que ser, it has to be almost the same fineness as cement. But usually what happens is when you grind clinker, the limestone becomes fine because limestone is usually softer. So it is not, actually what we find is the fineness of the cement LC3 is more than the fineness of ordinary Portland cement because the clay is easy to grind. The limestone is also easier to grind than the clinker. So we put in chunks. We don't grind and put. when you are grinding along with the clinker. Suppose you are blending, then the blend may be about 400 or 350 to be equal to the cement blend.
Porque eu aprendi que tem que o calcário tem que ser mais fino, porque tem a reação seria melhor. Isso que eu aprendi.
That is correct. If there is no clay. So here there is an calcium aluminocarbonate forming. But what you are correctly telling is if there is only limestone, then the limestone accelerates the formation of the calcium silicate hydrate. But here we are not looking at that. We are looking at another compound which is coming from the combination of this clinker, the clay, the kaolin in the clay and the limestone. So we are looking at the mechanism of calcium aluminocarbonate forming.
Thank you.
Professor, gostei muito da sua palestra. O senhor mostrou uma visão holística do processo, não nos preocuparmos apenas com o material, mas com os processos produtivos.
Muito obrigado.
E eu gostaria de...
César se apresenta também.
Sou o professor César Dair, do IDD, também diretor de Relações Institucionais do IBRACON. Professor, em relação a limestone, agregado calcário, que o professor falou, nem agregado, na verdade, o calcário, que não é utilizado na fabricação do cimento, e, em geral, nós trabalhamos, então, com agregados dolomíticos. Obviamente que estamos falando muito sobre a questão da carbonatação do concreto, o ataque por cloretos, porque temos maior incidência de problemas patológicos relacionados à corrosão de armaduras. Mas em questão, por exemplo, de reações álcali-carbonato, vocês têm estudado isso? Como tem visto isso?
No. I don't have much experience because we do not have dolomitic limestone in large extent in India. So our experience is very little. Possibly you have more experience than us.
Okay. Thank you.
Dolomita heavy and magnesium.
Yeah, magnesium.
Excuse me. May I try to speak in English?
Certainly.
Okay?
Certainly.
And you work with a specific kind of clinker.
Yes.
But if you change the reactivity of the clinker, it is not a good way to change the amount of addictions we can addict to the Portland cement.
Yeah.
The way to increase the reactivity of the clinker is not a good way to change the quantity of admissible addictions to the cement Portland.
As far as I know, from what is being done in the industry, it does not change things a lot. The reactivity is affected a lot by the fineness. So when we have different grades of cement in India, they are not changing the reactivity of the clinker, but the fineness of the grinding. So usually it's almost the same production line, and they are just grinding finer to increase the reactivity, but not changing the composition of the clinker.
It's not a good way to try. Oh. Ah, tá. Não, eu estou perguntando para ele se nós trilharmos o caminho do aumento da reatividade do clinker para poder aumentar a quantidade de adições na produção do cimento clinker, não seria uma boa linha de pesquisa, porque existem aditivos que aumentam a reatividade do clinker. E esse caminho possibilitaria uma adição maior de materiais como pozolanas, etc., mantendo as propriedades do cimento.
Well, frankly, I don't know. I have not seen much research on how the composition of the clinker affects the amount of admixtures that you can use. So I don't know. I don't know.
Thank you. Okay, obrigado.
Yeah.
Oi, obrigada pela palestra, professor. Eu sou a Patrícia Falcão-Bauer, da Falcão-Bauer, e eu fui aluna do professor Vanderlei John no meu mestrado. E um dos temas, eu estudei uma característica ambiental do cimento coprocessado. E aí, olhando todas as apresentações, a gente enxerga muito o copo meio vazio, mas essa maneira do coprocessamento